Hello there and welcome to my channel on chemistry lessons. If you find these videos useful, please make sure you like and subscribe. This video covers enthalpy of solution and calculations involving enthalpy of solution. So we're going to start off with a couple of definitions. We need to define enthalpy of solution and define enthalpy of hydration, and then we're going to look at constructing cycles and carrying out the associated calculations. So definitions. So it's worth pointing out at this point that I would teach this after Born-Haber cycles. So I'm assuming that we've already covered Born-Haber cycles and you know all the definitions associated with Born-Haber cycles. So two further definitions that we would need are enthalpy of solution, which is the enthalpy change when 1 mole of a solute fully dissolves in water. And there's an equation to represent the enthalpy of solution of sodium chloride. You can see the state symbols here are essential. And again, it is worth knowing whether values are going to be exothermic or endothermic, because some enthalpy changes are always exo, some are always endo. It turns out that enthalpy of solution can be either. Enthalpy of hydration then, that's when 1 mole of gaseous ions forms 1 mole of aqueous ions. And to show an equation, there we go, that's the hydration of sodium. So from sodium gaseous ions to sodium aqueous ions, and it's 1 mole. And this is always exothermic. And that's because bonds are being formed between the gaseous ions and polar water molecules. So there's a bond forming between water and the gaseous ions, so it's always going to be exothermic. The reason I stress whether values are exothermic or endothermic is in the pressure situation of an exam. If you are expecting an answer to be negative and you get a negative value, it does kind of give you a little bit more confidence. Whereas if you're completely unaware or unsure whether it's going to be negative or positive, you don't have that same level of confidence at the end of a question. So let's have a look at what an ionic lattice is. So way back in GCSE or possibly first year at A level, you look at what an ionic lattice is. Now some ionic lattices are soluble and some aren't, and we looked at the properties of ionic lattices in terms of conducting electricity, in terms of their melting points. But what we're looking at here is the ones that are soluble. So what happens during dissolving? So when a lattice dissolves, we can actually use enthalpy changes to show the steps that are taking place. So we could visualize this. Now, this doesn't actually happen. It doesn't turn into a gas before it dissolves, but in terms of enthalpy changes, we can visualize as the lattice breaking up into gaseous ions, which would be the lattice dissociation. And then what happens is bonds will form between polar water molecules and the ions. So we have lattice dissociation followed by enthalpy of hydration. Let's try and represent this on a Born-Haber cycle. So here we have 1 mole of ionic lattice. That can be any ionic lattice and it's 1 mole. So what we'll do first off is we'll dissociate the lattice. We'll turn it into its gaseous ions. And that's going to require a lot of energy. That's going to be breaking up the ionic lattice. We use these to discuss and compare the strength of ionic bonds in previous topics. And then what we do is we then hydrate those gaseous ions into aqueous ions. And quite often we need to do it to more than one ion. We need to do it to both ions. Okay, so it's the sum of the hydration. It's the hydration of the positive ion and the hydration of the negative ion. And you can see the way I've shown the diagram here, the enthalpy of solution is coming out as exothermic. So the sum of the hydrations, if that's bigger than the endothermic lattice dissociation, you can see that it's going to be exothermic if the right-hand side is bigger than the left-hand side. So for example, this arrow here is bigger than this arrow. That means overall we're going to end up with our exothermic enthalpy of solution. If it was the other way around, so let's just say this time the sum of the hydrations was less than the lattice dissociation, you can see that we now have an endothermic enthalpy of solution, and that's why the enthalpy of solution can be negative or positive. It can be exothermic or endothermic because it depends on which of the two values is bigger. If this value is smaller than this value, you can see that it ends up being endothermic. So let's look at some calculations then. So we can just use this equation, okay? You can just use the equation that enthalpy of solution is the enthalpy of lattice dissociation plus the enthalpy of hydration. So we could use this value here, we could use this equation. Enthalpy of solution is lattice dissociation plus the sum of the hydrations. There are actually three ways we can carry out these calculations though, okay, and I would teach all three and suggest you pick your favourite. So we can just use the formula. To remind you of the formula, it was enthalpy of solution is equal to the enthalpy of lattice dissociation plus the sum of the hydrations. So in this case, sodium chloride. So the enthalpy of solution is going to be equal to the lattice dissociation, which we are given is plus 776, and it's plus the sum of the hydrations. Now sodium chloride is going to involve one sodium ion and one chloride ion. So it is literally 1 times minus 407 plus 1 times minus 364. And we'll put that into our calculator. 776 minus 407 minus 364. And I get an answer here of plus 5 kilojoules per mole. So enthalpy of solution of sodium chloride is endothermic. And that's using the formula. So you can just remember that formula. Enthalpy of solution is equal to the lattice dissociation plus the sum of the hydrations. Now you do have to be careful that you're aware that sometimes you may need to multiply some of the ions by 2. And what I mean by this is if the lattice was magnesium chloride, for example, we would have 1 magnesium ion, but we have 2 chloride ions. So we would need to double the hydration of the chloride because it would be 2 moles of chloride ions. Okay, so we could also use Hess cycle to carry out this calculation. And we would always have the enthalpy of solution as the top equation. So in this case, it's sodium chloride, which is a solid. When it dissolves, it forms 1 mole of sodium aqueous ions and 1 mole of aqueous chloride ions. And this is my unknown value. I've been given a value for lattice dissociation, which is plus 776, and that's going to be forming gaseous ions. I've also been given the value of the hydration of sodium, which is from the gaseous ion to the aqueous ion, and that's minus 407. I've also been given the value of the hydration of chloride, which is from gaseous chloride to aqueous chloride, again 1 mole, minus 364. And now what I do is I apply Hess's law, and my root 1 is this. So I've got my start and my finish. That's my root 1, so it's x is root 1. Root 2 is this way and then this way. So root 2 is plus 776 minus 407 minus 364. Work that out and I end up with the same answer of plus 5 kilojoules per mole. The third and final method would be to use a Born-Haber cycle. So I'm going to sketch a quick Born-Haber cycle. Here we have enthalpy on a scale. I'm going to start with 1 mole of the ionic lattice, which in this case is NaCl solid. I'm going to dissociate it into its gaseous ions. That's an endothermic process. Sodium gaseous ions and chloride gaseous ions. That change there is plus 776. Remember, when we do a Born-Haber cycle, a movement up is positive and down is negative, because we do have an axis here of enthalpy. We don't have that axis when we do Hess cycles. And then what we're going to do is we're going to hydrate. We can either hydrate the sodium or the chloride. It doesn't matter which ones we do first. I'm going to opt to hydrate the sodium, in which case I have to leave the chloride as gaseous. So there's the hydration of sodium, which is minus 407. And then I'm going to do the hydration of chloride. Now the only thing is, when you're sketching these, you have to make an assumption at this point whether you think it's exothermic or endothermic. I've made an assumption that I think it's exothermic. Now we already know that's wrong from previous calculations, but you always have to make an assumption when you're doing this Born-Haber cycle, because this is the value I'm trying to calculate. This is my unknown, and I'm aware it could be negative, it could be positive. Okay, and now I'll follow out my calculation. I like to have a root 1 which is equal to x, so that's my root 1, my start and my finish. So that's x, that's my root 1 here, my unknown. Root 2 will be going up here, which is plus 776, then down minus 407, and then down again minus 364. And it is the same calculation. I end up with plus 5 kilojoules per mole. So it's entirely up to you which of the three methods you use. A lot of students do use the formula, and there's nothing wrong with that. My only concern is, if you do rely on a formula in the pressure situation of an exam, there is a chance you might forget it or you might be uncertain. My preferred method is the Hess cycle. So what I suggest you're going to do now is you're going to have a go at this next problem on your own. So I suggest you pause the video and have a go at this. And when you're ready to hear the answer, unpause the video. So this question is slightly more complex for a couple of reasons. Now I prefer the Hess cycle method, so I'm going to stick to a Hess cycle. So the first thing I'm going to do is to construct an equation across the top for the enthalpy of solution of calcium chloride. Now the first mistake students will make is they'll get the formula wrong for calcium chloride. It is CaCl2, and it's very common for them in exam questions to name the ionic compound rather than giving you the formula, because they know if they write the compound down, there's a chance that you will get the formula wrong. So don't make that mistake. Calcium chloride, CaCl2. And I'm going to turn it into aqueous ions. So I have 2 chloride ions here. And I've been given a value for the enthalpy of solution of calcium chloride. It is minus 141. I'm then going to dissociate my lattice into gaseous ions. Ca2 plus gaseous plus 2Cl minus gaseous. And that is plus 2237. I've also been given a value for the enthalpy of hydration of calcium is minus 1650. I don't have a value for this, and that's what I've been asked to calculate, is the hydration of chloride. Now I've got to be clever here, and I'm going to put 2x, because it's actually 2 times the hydration value, and x is going to be my hydration value. So now I'm going to use Hess's law. Now I've decided that I'm going to have my start point down the bottom. That's going to be my start, and this is going to be my finish up here. I always like to have my start and finish to just be one step and involve my unknown value. So I'm making sure my start, finish includes my unknown. So from start to finish, root 1 is this way. And root 1 is equal to 2x minus 1650. And that's equal to root 2, which is this way, which is against this first arrow here, look. So that's minus 2237, and I'm going with this arrow here, so it's minus 141. Rearrange this equation to get 2x is equal to. So that's going to be minus 2237 minus 141 plus 1650 is equal to minus 728. So x is equal to minus 364 kilojoules per mole. The biggest mistake students make on these questions is to get the multiples incorrect or to make a mistake with the direction of those arrows. Okay, so hopefully you found that useful. If you have, make sure you check out the other videos and like and subscribe. Thank you.